Okay, so we're about here. We started talking about smooth evolution of observables and the Koopman generator. And today we're going to continue on this topic, and then we are going to venture into understanding the concept of state space partitions. This is a topic that doesn't get covered as much in classical geometric dynamical systems courses, but it's quite important in the context of applications of Koopman operator theory to dynamical systems. So I'll spend some time discussing this today as the part of the background that we are building, and then depending on time, today we are also going to talk, really review some of the aspects of the asymptotic dynamics of dynamical systems. We are going to talk about limit cycle attractors, quasi-periodic attractors, and chaotic attractors. I don't think I'm going to quite get there today, but the reason for this lineup is we'll start talking about systems which have fixed points as attractors. And as you're going to see in the class, we're going to carefully go through linear systems that, for which a fixed point is really the only viable attractor, except if you consider systems that have, cycles everywhere. But of course, they don't have an open set that attracts to them. So I'll discuss a little bit these concepts of that go back to geometric theory of dynamical systems, but then we're going to go through types of dynamical systems that are increasingly hard as far as their dynamics is concerned. So start with fixed points, go to limit cycle attractors, quasi-periodic attractors, and then ultimately chaotic attractors. In this introduction, I'm still going to discuss transient dynamics as well, so that we understand how dynamical systems get to their attractors, and that's going to be a topic, but I don't think we're going to get there today, probably next time. All right, so let me just review briefly a couple of things that we've done last time. We spoke quite a bit about aspects of eigenfunctions of the Koopman operator, and it is kind of a typical result that we were talking about. If U is a Koopman operator, then we assume that F is a subset of all C-valued functions on the state space M that forms a vector space, which is also closed under pointwise products of functions and contains this constant function that's always in there. And under those assumptions, if you find two eigenfunctions as Koopman operator, you're going to find many of those because the product of any of these eigenfunctions will be an eigenfunction. Again, it's going to belong to that space by this property that it's what we call an algebra. It's closed under pointwise products of functions. And then you can certainly get from a finite amount of information, so finite number of eigenfunctions, to very often a sufficient number of eigenfunctions to actually span your space. And you will see that's going to come handy when we do one of the essential concepts, do a discussion of one of the essential concepts in Koopman operator theory, and that is spectral expansions. So right now we are doing an introduction, but pretty soon we are going to be talking about how to use these eigenfunctions in analysis. And then we finished last time by talking about a couple of things. We took this function g, that is a function of two arguments, time t, and then a point in state space. And that function was really the composition of g with stx, or in other words, it's what happens when you act with a Koopman operator for a continuous system at time t on a function g that is defined as a function on state space, meaning a function of these x variables. So that's what we denoted by g of t and x as in contrast with g of x, which is just quote unquote a static function and observable in state space. And we proved that provided g is smooth and your flow is smooth, then derivative of g with respect to t is the grad g, and full differential geometric terms, this would be really a derivative of g. We would often denote it by d instead of this nabla symbol here, dotted with a flow. So that's the formula. The evolution of g in time is given by a partial differential equation of this form. And I mentioned several times that this really tells you again that information, when you consider this evolution, Koopman evolution, UTG's g of t and x, is propagated backwards. So let's read the meaning of this equation. It says the following: the change of this function g at point x at time t, the change of g with respect to t is provided to you by the change of g in the direction of f. Yeah. So what that means is you look at point x, draw something. You look at point x here. Take a look where f is taking x. And now you figure out what the grad of g is. And so the change in g under the flow of f is precisely the change in g that you're going to see at this point x at time t. So that really means that you see what g of t and x is here at time t, and you kind of propagate that information backwards and assign it to an initial point. So once again, as I pointed out before, these Koopman type evolutions give you information that is propagated backwards. The trajectory goes forwards, you pick up what the value of the function is, and you propagate it backwards along trajectories. And as we go on, I will mention that the Koopman operator theory can be formulated for stochastic systems, so not only for deterministic ones. F here is a vector field, a deterministic vector field. You could add noise, various types of noise to this. You can formulate a kind of similar operator. And in the context of specifically stochastic differential equations, sometimes the analogous operator to this is called the backwards Kolmogorov operator, because Kolmogorov defined it for a particular class of stochastic processes. There are 2 points to what I'm saying here. One is that backward propagation that I'm kind of repeating and trying to sort of get it established as a feature of Koopman evolutions. And the second point is that the theory that we are developing is really not restricted only to deterministic systems, but can be extended for systems with noise, and I could say relatively easily. So the formulation is very similar to the kind of formulation that you're seeing here. And in various physics and engineering applications, this is quite important. The reason being that you always have noise present in the data, and how your formalism deals with noise is an important aspect of how useful the formalism is. And it turns out that this Koopman operator formalism is quite easily extended and robust, let's say, to the addition of noise. You don't need to change your perspective in order to proceed with similar analysis. And then we gave, as the last thing, one example of just a rotation on the circle. Theta dot is equal to omega, where omega is some positive number, really the rotational speed. And then the equation that turns out to govern the evolution of G was the wave equation, whose solution is that G at time t and theta is G at theta plus omega t. If you just plug this into here, you're going to see that that is the correct solution. And now you see that to obtain G at any time t at theta, you just need to go along a trajectory of this vector field, and that trajectory takes you to theta plus omega t. Theta plus omega t is just a solution of this equation starting at time t, starting from initial condition theta. You look up G over there, and that's your time-dependent G of t and theta. So it's basically propagation of values of function G to the left, provided the value of theta increases in the clockwise sense with speed and back. All right. So let's go a little bit further, and we will see that what we derived, that expression of partial G with respect to t, which contains something like this, actually shows up when you consider the following. So let's take the function G, some observable, and then act on it with the Koopman operator ut. So utg minus g is the object that we want to consider, and let's divide it by t and take a limit when t goes to 0. That's pretty simple to compute. So that's just by definition, utg is g of stx, a composition of g with st. We're subtracting g of x, dividing by t. This we redefined as g of t and x. So that composition is g of t and x. And this then is g of 0 and x. If you look back at our definitions. And so clearly then, this is the definition for the derivative of g of t and x with respect to t at time is equal to 0. But when we look back at our previous derivation here, that is precisely f dot grad g taken at t is equal to 0, g of 0 and x, g of 0 and x is u0g, which is just z. The Koopman operator acting on the function g at time 0 gives you back that function, its identity, right? Nothing changed at time 0. So when Koopman operator acts at time 0, function g, it gets back the function g. So what did we get here? We found that this limit here of the evolution of the observable g under the Koopman operator minus g itself divided by t is precisely f dot grad g. And that gives us an opportunity to say, okay, let's define this operator A acting on G as precisely f dot grad G. And for the reason that's going to become clear very soon, this thing here, f dot grad, is called the generator of the family ut. So family meaning it's a set of operators parameterized by the time t. So the family of Koopman operators parameterized by the time t. And this is again an operator. What is an operator? You take a function, you produce another function. So if you think about this, you take a function g, take its gradient, take an inner product with the vector field f, you're going to get another function of x, right? So that's an operator again. And it turns out that A and G are connected in a very profound way. Of course, we did get to A from, pardon me, A and UT are connected in a very profound way. So of course, we got to f dot grad operator from taking this limit of action of the Koopman operator on a function, so they should be in some sense. But let's go first to talk a little bit about a property of ut in the case when f is smooth and globally Lifshitz, meaning the solutions exist and are unique. And in that case, it turns that this family ut of operators is actually a group. So a group needs to have several properties: identity, associativity, closedness, and inverse. And this formula here says, okay, let me take the member of this family of operators u at time t plus s. So two different times t and s, both in R, both real numbers. So that is equal to UTUS. So you first advance your function that you're acting on with US itself, and then you act on it with UT. But recall what the definition of UT is. So UTG is G composed. I'm going to have to erase this. Is G composed with ST. And what is ST? Well, ST is the map that takes us from some initial condition X of the flow on the state space M to the final position. So ST X. And now the point is, main point here is that if I go from X to STX and then decide I'm going to go a little bit further for another duration of time S. So this interval here is during time S. It really doesn't matter whether I went first for time T under the flow and time S, or I first went for time S up to here, and then for time T to this final point. Because the total time it's going to take me from here to here along the trajectory is, of course, always the same. So whether I split it into first T seconds and then the S seconds, versus I split it into S seconds and then T seconds, it doesn't matter. And so what that means is that the application of this mapping ST is actually commutative, right? You can first apply SS and then ST, or you can first apply ST and then SS. And what that leads to, since the Koopman operator is just a composition with the flow, is that you can first apply the Koopman operator for S seconds and then the Koopman operator for T seconds, or you can first apply the Koopman operator for T seconds and then for S seconds. And then this gives you commutativity. So this is actually a commutative group. And that's a nice property, but this is valid as long as F is only a function of X and not a function of T. And I see that Nibod has a question. Go ahead.
Thank you, Professor. I had a question that if the dynamics weren't smooth, in practice, say like for hybrid systems, does that mean that we'd be pretty much relying on the Koopman semigroup itself and not even look at the generator?
Depends. There are actually hybrid systems in which you can easily take a your question is about the generator.
Yes.
So again, depends. So there are hybrid systems that are piecewise smooth, right? So in that context, you can actually get piecewise generators to take you from one place to another and partition the state space. The other part that I thought you were asking, and it's kind of an interesting question as well, yeah, how does this whole thing here depend on things like existence and uniqueness? And there are hybrid systems in which definitely you have existence and uniqueness for all time. So this is completely valid. But the answer to the first part of your question is very often you can split your state space into the parts on which the generator is still valid. But this is actually kind of an important question from the following perspective. I usually say, well, this is the case in the introduction where we are dealing with smooth systems, and in a lot of our discussions we're going to be dealing with smooth systems, you know, to explain the basic concepts in the theory. But really it's useful to start not with the generator but with the evolution itself, with the Koopman operator itself, because of course you can define the Koopman operator for pretty much any evolution out there, be it hybrid or smooth or non-smooth or whatever. You can even define it for, you know, control type systems in which from one point you can reach a set rather than just a single point. So it's really useful to think at this level. What I'm deriving the generator equations for is to show you one example in which we connect to a variety of different topics that you might remember from, you know, fluid mechanics, where these kinds of partial differential equations appear, and have some intuition about and how this actually acts on functions, and a little bit more familiar example, because of course the Koopman operator itself is a bit more abstract example than these differential operators. Does that answer your question?
Yes, Professor. I had a second question, if time allows. This one goes back to the existence and uniqueness. If the dynamics aren't Lipschitz, and say something like a finite escape time, x dot equals x squared. So one question is, if it was x dot equals negative x squared and it wasn't time reversible, then would the limit above be one-sided?
Yeah, so of course you have the action of the Koopman operator for all the time that the solution is defined, up to the point where you get an escape, right? You hit infinity at some fixed time. Now of course, as far as the state space is concerned, your evolution of a function, if you look at it spatially, is going to exist everywhere, right, on that state space. So in that particular case, you have a finite time t up to which you can consider the evolution, right? And at that time t, you have an escape at infinity, and that's kind of the end of the evolution. Does that help?
Yes, Professor. Thank you.
Very good. Okay. By the way, this is also an interesting question, because in many cases you can have a particular transformations that remove the singularity, but we're going to discuss that briefly when we discuss the topic of conjugacies. So we are going to go a little bit further along those lines. And so for the rest of the class, if you remember in ME 215, for those of you that you have taken it, we had this example of x dot is equal to x squared, in which you have a finite time escape to infinity. So not all ordinary differential equations possess the existence and uniqueness of solutions. This is why there are these restrictions here. Okay, but now we're at a place where we have something that we call the generator, for the reason that is going to become clear in a moment. And we have proved that our family of Koopman operators under all these conditions is actually a group, and at that it's a commutative group, and that's nice. So this operator A, again, you can go back to your multivariable calculus. That's a linear operator. Again, if you put as its argument not G but some C1, G1 plus C2, G2, it would split into action on G1 and G2 and multiply by appropriate constants. So it's pretty simple to see that A is again a linear operator. And it's really this operator of differentiation along the trajectories. So in multivariable calculus, we learn about directional derivatives, and it's indeed a directional derivative in the direction of the vector field, but it's defined, of course, on the whole space, M. Right. So let's do something specific, because you're going to start seeing the meaning of the notion of the eigenvalue of the Koopman operator in slightly different light. So let's plug in into that limit that we have considered above an eigenfunction phi. Let's assume that an eigenfunction exists, and we are going to plug in phi and consider ut phi minus phi divided by t. So ut phi, by definition, because phi is an eigenfunction, is e to the lambda t phi. And so now, if I take phi out, I get e to the lambda t minus 1 divided by t. Now, by Taylor expansion of e to the lambda t, I know it's just 1 plus lambda t plus higher order terms divided by t. And that ends up giving me the limit when t goes to 0, which is just lambda phi. So what I've used here is that e to the lambda t, just like here, is some lambda to the k, t to the k divided by k factorial. Here I'm going to use it in a very different sense. So the first term here is clearly just 1. The second term is lambda t. 1 and minus 1 cancel. The third term is depending on t squared, right? So t squared divided by t is just t. That goes to 0 when t goes to 0. And so what is left is just lambda here times phi. That's the result that we get. And so now we have this term here is just phi dot, fair? It's just the derivative of phi with respect to t. Now that we know by definition is f dot grad phi. And we named this operator f dot grad. We named it A and called it the generator of the Koopman evolution. And now we proved that A, acting on an eigenfunction of the Koopman operator, on a smooth eigenfunction of the Koopman operator, is just lambda phi. Great. This should look familiar. If A was a matrix and phi was a vector, this would just tell you that phi is an eigenvector of A with an eigenvalue lambda. And so now it becomes a little bit clearer why, ut phi being e to the lambda t phi, why we call lambda as an eigenvalue. It's really related to this property of the generator, where now you're seeing the classical eigenvalue, eigenvector expression. Is just that phi here is what is called an eigenfunction, because it doesn't have a finite number of components. Now we have to mention some properties of A that we're not going to prove because it's a little bit early for some of the technical aspects of this in the class. But if you assume what is called a uniform continuity, so this is a notion of continuity in Banach spaces. If you want to look it up, the great book to look it up and is this book by Engel and Nagel on one parameter semigroups for linear evolution equations. In that case, this Koopman operator here, ut, can be written as e to the at. This looks familiar, I hope. If you have a linear system, x dot is ax, then e to the at is the solution to that linear system where A is the matrix, right? If you remember that. But here, this looks a little more profound, because A is actually an operator. It's f dot grad. And ut is also an operator. So you could say, what the heck? What do we exactly mean by the right-hand side here? And what we mean is essentially a Taylor expansion. So we define e to the at as the sum k is equal 0 to infinity, a to the k, t to the k, k factorial on the bottom. And this condition here allows you to prove that that's a valid convergent expansion. And then the ut, the Koopman operator, and a are related in this in somewhat familiar form, let's say, because you've seen it before in the context of linear systems. And I will show you how it applies to linear systems in a moment. But let's first utilize that, what we've just defined. Let's take some vector of observables. That's boldface G. That is a function of some point P on the state space. You will see in a second why I'm not using X here. That might be slightly confusing at this point, but at this point, we need to start making a difference between points in state space and X, which, as you're going to see, is going to be really a notation for the functions that are state observables. It's going to become clearer in a moment. But okay, taking that P is a point in our state space M, let's consider the action of the Koopman operator on G. As we have from this formula, ut is e to the at. Expand e to the at in this form, and now you have a scalar t to the power k, so that's time to power k. You have an operator. I have actually a power of the operator. So let's pull t to the k up front, divide by k factorial, and then we have f of p dot grad to the kth power. So this is k concatenated applications of this operator acting on G. Okay, so far so good. So we have a formula as to how ut acts on G, provided we know the associated vector field that we started from. That's the benefit of what we have just derived. There is an infinity of terms, but we do have an expansion. It's not, I repeat, not a spectral expansion. Spectral expansion is going to mean something else. This has the spirit of the Taylor expansion, right? But let's see how it works. And it's going to give you a good feeling, I hope, as to how to work with this formalism of operators, rather than working with the formalism that we are used to, ordinary differential equations on state space. So let's go through an example. So let's take a linear system. X dot is Cx. C is an n by n matrix, and X is a vector in Rn. So we're starting from familiar grounds. And then now, remember that the generator itself, A, is f dot grad. What is the vector field F? Well, it's just C matrix acting on X. So we have Cx dotted with this gradient operator here. All right. So now this notion of P versus X of P. E to the at acts on functions. So I really should consider this X as an observation on the state. And that's a key shift and a point of view that I like you to adopt at this point, right? So don't think of X as just variables that, describe some n-dimensional vector space. Think of them as functions. So x1, let's say we have the first component of this. So you have some n-dimensional space. And usually we denote this, axis, let's say by x1. But take a point P in this n-dimensional space. What is x1 of P? It's the value that your sensor would observe if it was measuring how far along on this particular axis P is. So x1 is really a function, right? A function is an association of a number with a point on the space you're looking at. And so x1 is really a function on the state space, instead of being this variable here that we are used to. So is x2, so is x3. So x itself, boldface x, is a vector of functions, or in other words, the vector of observables that will provide us with n numbers if we feed it an argument p. So if you take an argument p and apply x to it, then that's going to give you a sequence of n numbers that will describe that point. And p is an abstract point, has nothing to do with a number. It's just an abstract point in the space that you can describe by n numbers. All right, so now we know that x are actually functions, and Koopman operator can act on functions. So we are set up to consider this equation, set of ordinary differential equations that are now equations that tell us how functions evolve. Now, the grad applied to x is just identity. Think about this. The gradient here consists of partial derivatives. For example, partial with respect to x1, partial with respect to x2, and so on. But x itself contains x1, x2, and x3. So partial x1 with respect to x1 is just 1. Partial x1 with respect to x2 is 0. So this gradient here is just identity. And now A, our operator, acting on x as a set of functions, is by definition Cx dotted with grad x. But grad x is identity, so A as acting on the functions x gives you C acting on x, because this part here is just identity. All right, so we proved that A, our operator here, acting on x just once, is Cx. So far, so good. So now let's use the expansion e to the at x on p. This is actually what we proved, or rather mentioned, is ut. So this is the action of the Koopman operator on functions x. All right, that expansion is a to the k, t to the k, k divided by k factorial, acting on x. So again, let's write out a. That's Cx dotted with grad. That's a. Applied k times. So k times. So on power k, acting on x. All right. So if k is equal to 0, so k goes from 0 to infinity. If k is equal to 0, this is 1, and this is 1, and this is 1. So what I get back is just x, right? If k is equal to 1, then I get t divided by 1 Cx dot grad to power 1. I already got that formula, so I get t to the power 1 divided by 1 Cx. That's k is equal to 1. K is equal to 2, just slightly trickier. You have to apply this twice, but you can again use the fact that this is identity. So I'm going to get Cx dot grad Cx. That is going to give you the second power of C acting on x. take the third power, you're going to get the third power of the matrix, and so on and so forth. And look at the expression that we got. You hopefully recognized it from your previous classes on control and dynamical systems. It's just a familiar solution of this equation here, which is this itself is equal to e power to c t. That's just the Taylor expansion of e to the ct, which of course we know is the correct solution of this. What's the difference in what I've done so far? I worked entirely in the context of operators, right? The way the solution is usually presented, this e to the ct as a solution of that, obviously I need to write x as well. The way usually this solution is presented is just as an answer, what you call ansatz. Basically, take this as a solution, plug it in, and you see that it works, right? That's the idea. What we've done here is something quite different. We define this operator, right? Then we use the fact that we know something about how the Koopman operator acts on this set of functions x, in particular through this expansion. Then we worked through that expansion and came back with a correct evolution of our observables x. So it was done in a systematic fashion, observing that you have a set of functions that you're observing, twice. So what I really meant to say, starting from the point that you have a set of functions that you're observing, and then use an expansion to come and derive a solution to this set of ordinary differential equations that we started from, and that being the correct solution. You could say, well, couldn't you do that for an arbitrary nonlinear system? And interestingly, that's true. We certainly can. We can write for now the system x dot is f of x. That the solution can be written as e to the at x of p. You can consider this x of p as, if p is an initial condition, that's going to give you the initial condition for this evolution. So e to the at x of p, expand, and if you work through it a little bit, you're going to see that the first term again is x of p, just like I argued before for the linear system. That's the k is equal to 0, where this is 1, that's 1, and this is 1, and so you're just left with x of p. And then you have a term f of pt. That's when k is equal to 1. Grad of x in that case is identity. So what is left is t to the first power. K factorial, k is 1, so that's just 1, times f of p. Now let me stop there and notice the following thing. If I neglected the third term and the fourth term, you would be left with x at time t is x of p plus f of pt. For very small time t, do you recognize that formula? Have you ever encountered it before? Do you remember Euler formula for solution of ordinary differential equations? So that's precisely it, right? This first up, if you stop this at the first order, you will get back the Euler formula. But this whole expansion actually has a name as well. If you worked in differential geometry, it's called the Lie series. So that's usually derived by differential geometric means. Here we have derived it from entirely from the perspective of operator theory. So anyhow, we have come to the point where, in principle, you can use Lie series for solutions of ordinary differential equations. It's not very commonly used, but in principle, you can take time t, very small and try to get the next position of your system from this formula. But and in general, this expresses a general solution for an ordinary differential equation. Now we are going to argue and see that another type of expansion, a spectral expansion, will do something for asymptotically long times that is quite interesting. So you get quite a bit of additional information if you take a slightly different approach that is, I would say, more operator theoretic in nature. Although, of course, we did work with operators here and derive this formula, you will see that things kind of simplify quite a bit when you start using eigenfunctions, which we really haven't done here. This is the formal expansion that doesn't use the specific, what we call spectral properties of the operator. So when I say spectral, I really mean using eigenfunctions and eigenvalues. That's the idea. Or you will see that there are other parts of the spectrum that are not eigenfunctions and eigenvalues, but using those objects like eigenfunctions and eigenvalues is what I mean when I say spectral analysis. And this doesn't have any of it. And so while it might be useful for calculating solutions of ordinary differential equations in relatively short time periods, you will see that there are benefits of taking a spectral point of view.